Okay, so everyone is with every the coffee, which is okay because that's the rule that you cannot drink or eat here. So it's my pleasure to introduce Armando, who arrived just yesterday after a long way trying to come here. And Armando will give a tutorial based on demands that if you remember when I asked what you would like to see, there were so many demands saying like, hey, we would like to see tutorial on neurosymbolic programming. So Armando, thank you for answering requests, and here it is. So please go ahead.
All right. Hi, everybody. Good morning, and good to see all of you. So I'm going to be talking about this broad space of what we call neurosymbolic programming, which is kind of a subset of a bigger space of neurosymbolic learning. It's essentially learning meets program synthesis. And a lot of what I'm going to be talking about here is work from my group, as well as Swara Chaudhury's group, who also helped produce a lot of the content that we're going to be talking about today. So at the very high level, our goal is we want to be able to learn models, but in a way that allows us to capture symbolic knowledge about the world, and in particular, symbolic knowledge in the form of program structure. We want to be able to learn things that look like programs, or at least that have part of them that look like programs. But at the same time, we don't want to completely give up on a lot of the expressiveness of deep learning and this ability to learn fairly arbitrary functions with very little background knowledge about what we want to learn. And so we've been experimenting with different ways of combining these two very distinct modes of reasoning. And what I'm going to talk about today is a bit of an effort to impose some structure over what is a very large space of algorithms and combination of algorithms that we can use to do this style of learning. And so what we're going to do is we're going to start from a set of building blocks, and then we're going to talk about how these building blocks can come together to produce more interesting, richer algorithms for particular tasks. And so the first building block, one that is very familiar to us from a lot of our prior work on program synthesis, is just this idea of program search. We want to be able to search these very large spaces of programs with discrete structure, with building blocks that might have been provided by the user. And we want to be able to do this search efficiently and potentially in a way that takes advantage of a lot of the learning capabilities that we have with us today. The second important building block that we're going to be talking about today is this idea of relaxation. The idea here is that you start with something that is symbolic, something that might be very discontinuous. And from that, we want to be able to relax that into a continuous representation, a representation over which we can, for example, compute derivatives so that we can do numerical optimization very efficiently. This representation might be in the form of neural networks, but it doesn't necessarily have to be. And we'll talk a little bit more about that as we go on with this tutorial. The other really important building block here is what we call symbolic guided deep learning. And the idea here is that we have some goal, we have some high-level goal. And what we want to do is we want to learn some neural network that satisfies that goal, but that is also guided by some symbolic knowledge provided in the form of either a full program or more often in the form of partial programs or in the form of building blocks from which we're going to build these programs. And so the idea is you can think of this as a form of regularization. You're using the symbolic knowledge to control how this neural network is going to be able to generalize from the initial goal that is provided to it. Another important algorithmic building block is this idea of distillation. So we have some goal, out of that goal, we learned some neural network, but for some reason, we're not happy with just a blob of neurons that maybe or maybe not satisfies the task. What we want to do is, from that blob of neurons, be able to produce an actual symbolic program. And as we'll see today, there's many reasons why you might want to do that. But one of them is that by imposing more structure and by having the domain knowledge that you can impose in the form of, for example, the domain-specific language that you use to build the program, you have much more control over the function that you learn and how that function is going to generalize to unseen cases. And the final building block that we've found very useful and we've been exploring a lot is this idea of symbolic abstraction, being able to take many different symbolic representations, being able to identify common structures within the symbolic representations, being able to abstract that common structure into a new component that then allows us to represent this. And so even though this is a purely symbolic operation, what we found is that it can actually go a long way in terms of helping some of these combinations of symbolic and neural algorithms have some of the benefits of the purely neural algorithms that can sometimes be lost when you start introducing some of these symbolic structures. So this is kind of a high-level overview of the different building blocks that we're going to be talking about today, and then we're going to talk about how these building blocks come together. Are there any questions so far? I think we have a small audience. We can make this a little bit interactive, so please feel free to interrupt and jump in if you have questions. Yes?
Every neural net and just write it as a program. So I don't quite understand the distillation. Every neural net I can, instead of using whatever representation, I can write it as C code, right?
Yeah, absolutely. And really the distinction that we're making here between the neural network and other kinds of programs is this ability to impose more structure over the computation, to be able to capture, for example, repetition, to be able to capture recursion, or even just to be able to capture domain knowledge in the form of, hey, here's this building block, this algorithmic building block that has already been packaged into a primitive that I know I want to use. Now, but admittedly, this is a fuzzy...
unless a symbolic program is somehow much significantly smaller or significantly have more structure than the neural net, just to say I'm going from neural net to a program, I don't see what it accomplishes, unless you add some quantitative notion by how much I've gained by doing this distillation.
Yeah, absolutely. And we'll see some examples of that shortly. This is admittedly a fuzzy line in the sense that, for example, in the neural network, you can also impose some structure in the computation. Convolutional neural networks are a great example of that, right? Where yeah, exactly. You have some notion of symmetries. The thing that we bring to the table in this case is much more generality in terms of the building blocks that we bring to the table. And in particular, the fact that when you're talking about neural learning, usually you commit to a structure to begin with, and then it's really all about using numerical optimization to discover the parameters. Whereas when we're talking about these programs, we're actually talking about the situation where we don't know the structure and where we are actually trying to discover that structure among a large space of possible structures. So let's start with the program search. So, in the spirit of this being a tutorial, this might be a little basic for many of you, but just to lay the groundwork of what we're talking about, right? So one of the big important building blocks is this ability to search a large space of discrete structures in order to find a program that does what we want, right? This is what program synthesis and the program synthesis field has been all about, or maybe we can say was all about, basically between 2005 and about 2017 or so, right? Just discovering new ways to search for programs very efficiently. And there's a lot of lessons that we learned out of that. For example, one of the lessons we learned is that types are actually a really, really good way to prune the search space, right? One of the things that they allow you to do is to start constructing programs and to be able to tell that a program that you haven't even finished constructing is wrong, right? It's wrong because it fails a type check. In the same way that an IDE can show you an error in your program, a type error, even before you have finished writing the program, right? This ability to rule out partially completed programs, removing large space of programs in one shot, turns out to be very, very valuable. In a paper actually back in 2018 from Suarez's group, they quantified the effect of using type system in order to prune the space of programs that we're generating. In this case, this paper was focusing on a particular class of list manipulation programs, but you can see a really dramatic effect in the sizes of the effective sizes of the search space with and without the pruning that you got from the type system, right? And this by having control over how you define the type system and the expressiveness of the types you provide, you can actually push this really far. But types and a lot of the tricks that we learned between 2005 and around 2015 will really only get you so far, right? When you're searching these very large combinatorial spaces of programs, as soon as you start trying to generate larger programs, you very quickly run into a brick wall. And so one of the big ideas more recently has been the use of neural networks to learn how to generate these programs. The idea is that you can learn the distribution of programs. You can even learn the conditional distribution that matches your description of the problem to the space of programs that you're trying to generate. And in that way, you can run a very focused search. And the community explored lots of different approaches to do neural guided search between, let's say, around 2015 and 2020. There's a big space there about exactly how you represent your programs, exactly what kind of neural architecture you use. Today, a lot of that has been somewhat subsumed by the rise of large language models. These are really today the most popular approach to defining these conditional distributions over programs. And even though in principle, you can just take an LLM, give it a prompt, have it produce a program. In practice, what you find is that it's still very important to actually think of these as a search process, right? The neural network is really just capturing a distribution over programs, a conditional distribution, and you still have to search that space. Now, just to give a really, really high level overview of what we're talking about here when we're talking about these LLMs, one of the things that made this kind of models very powerful is this autoregressive training approach, right? The idea is that what we're going to do is we're going to have this model that is trained on long sequences of text, which might be articles from the New York Times, might be programs from GitHub, might be, as it is nowadays, the entire output of human text production over the last couple of centuries, basically lots and lots of text. And what you're doing is you're training this model so that given a sequence of tokens, it is going to produce the next token in the sequence, the most likely next token in the sequence. And so in the beginning, when people started working on this kind of approaches, there were big question marks around, whether you could actually produce even syntactically correct programs, let alone programs that actually worked or did anything. But today, these models are actually quite capable of producing code. Not quite as capable as a lot of the hype would have you believe, and I have an entire other talk about many of the shortcomings of LLMs for code, but they're capable enough for our purposes. One of the things that is very significant to keep in mind is that as they are producing these next token, they don't actually just produce one token. What you get out of the model is essentially a vector that tells you a probability for many different tokens, for many different possible tokens. And so what this gives you is actually a distribution over tokens. It's not just producing one sequence. And there's many different strategies that you can use once you have this model to actually search over this space. Today, the thing that is most common is to actually just randomly select from these tokens based on the distribution that comes out of the model. And in fact, if you're using these models through an API, usually you have a temperature parameter that essentially determines how biased the distribution is going to be towards the most likely token. And so if you have a very low temperature, then basically with very, very high probability, you're just going to pick the most likely token. If you have a very high temperature, you're going to get a much more uniform distribution where you're more likely to pick other tokens in that distribution. And so from the same model, from the same sequence, you can actually sample arbitrarily many strings out of these distribution. And so by training this model with very, very large amounts of code, you can actually get models that can actually do a somewhat decent job of mapping the context and mapping even natural language descriptions of the text into these distributions over programs that you can search in a variety of ways, taking advantage of the fact that unlike most of the other uses of LLMs, when you're generating code, you can actually test that code. You can actually apply the whole toolkit that we have for trying to see whether a code actually does what we want or not. The other really big idea within this space is the use of reinforcement learning in order to either fine-tune some of these models or in order to train some of these models from scratch. And reinforcement learning is based on an approach where the idea is you have some state, you have your neural network that is deciding on some actions that are fed into an environment that based on the actions, it tells you what the next state is going to be and also gives you a reward that tells you how well you're doing. And in the context of program synthesis, usually the state is just a program or a partially constructed program. And the action that you take is just the next instruction or the next modification that you're going to do to the program. And the environment is whatever testing infrastructure, whatever infrastructure you have in order to check whether your program is doing the right thing or not. In general, these kind of schemes do better if you can have a reward that isn't just correct or incorrect program, but that can give you a sense of how close this program is to actually doing the right thing. We actually wrote an early paper on using this kind of approach to program synthesis. This kind of approach works particularly well for domains that have the property that you can look at the output, and the output itself has a lot of information about the structure of the program. So for example, drawing domains are very nice, right? If I know that my goal is to produce a shape like this, I can tell that there's probably going to be a circle in there, and there's probably going to be some rectangles in there. It's actually a very nice domain for this kind of approach. Domains like arithmetic, for example, tend to be not so good for this kind of approach, right? Just knowing that the function that I'm looking for is going to map 3,536 to 5,237 tells me basically nothing about the structure of the arithmetic operation that I'm searching for. But for this kind of domains, this actually works pretty well. And so you have a goal, you have some initial state, which in this case is just an empty canvas. And the neural network suggests a next instruction, a next command to produce. And so you can feed that to an interpreter to produce the new state. And at every step, the interpreter keeps track of what the current state is. And the neural network takes this information about the current state, the goal of the program, to suggest a new operation. So these are some examples of the kind of techniques that you can bring to bear in order for the search. One of the things that is quite valuable about using reinforcement learning to train this is that in addition to just the policy that at every step tells you with what probability you should choose different actions, you can also get a value function that can actually look at a wavefront of possible options and tell you which one of those is most likely to be completable to a correct program, right? And that can actually be extremely helpful. Here are some examples of the kind of programs that we're able to generate, both for 2D drawings and 3D drawings, essentially from a specification. You can see that the model, it doesn't always get it completely right. Sometimes it misses some details in those drawings, but it actually performed in this case much better than a model that was just trained on input-output examples. Yes?
Why this is good? Is it because it's easier to quantify the distance somehow?
It's a combination of this ability to quantify the distance, right? To say, yes, this drawing is closer to the target drawing from a different drawing that I want. And this quality, internally, we call it transparency. It's a bit of a fuzzy notion that tells you to what extent can you tell from the output something about the structure of the domain. It turns out, actually, another domain that has this transparency property is the flash fill type domain of text manipulations. It turns out, by looking at the structure of the output and the structure of the input, it tells you a lot about the kind of substring operations that you're doing. And in fact, we also applied this. Oh, if you want to know my salary, I probably should quiet out my alerts.
The other one. This one looks
that one looks compelling. We'll open it at the end to surprise.
This live transformation actually inspired by work of Brett Victor on his work on the live programming. He was actually using, I don't know if you have seen, he was using.
I've seen it before.
Yeah.
This, so if you're asking about the actual.
Yeah, like REPL loop and everything, yeah.
Yeah. So this, I mean, this idea of this redeveloped print loop is kind of a very old idea from, interactive programming, right? And the idea that you can, usually when people write programs, they don't just write the full code all at once and hope for the best. Sometimes they do, and unfortunately, then the code you get doesn't work, right? You write something, you run it, you look at what happens, you figure out what needs to change about that code. You do it one step at a time, and so giving the network this ability to look at this partially completed program and to look not just at the text that it has produced so far, right? This is one big difference here when you're dealing with just a traditional language model. The only thing it gets to see is the text that it has produced so far, right? But by actually having an interpreter in the loop, then you can actually also see what happens when you run that text through the interpreter. You get this additional information. And there is a lot of follow-up work in this space that combines large language models with this kind of approach in order to get actually quite good results. And one of the things that we did as part of this work too was actually to explore lots of different strategies for how to deploy these policies, right? So you have this policy, it gives you this set of probabilities about which action you should take next. You have this value function. It turns out you can use them in many different ways. You can use A star, for example, and just use the value function as your heuristic for A star. You can do what is known as a beam search, where at every point you keep the K most likely programs that you have seen, and you throw away everything else. And then from those K programs, you do another step of adding commands to those programs. You look at all the possible commands that you can add for each one of them. And again, you prune to keep the K most likely programs. What we found here is that actually the search strategy that worked best was sequential Monte Carlo. It's just a sampling algorithm that happened to work pretty well in this domain. So this is kind of a wind world tour of different search strategies and different both fully symbolic as well as neurosymbolic search strategies. But that's just one of the core building blocks that we have here. The next building block that I want to talk about is this idea of relaxation, starting with a program that might be very discontinuous, and then producing a new representation that is continuous, differentiable, that allows us to do numerical optimization to, for example, do parameter search. And there's actually two broad classes of approaches that we use to do this. One is to do it symbolically. This is essentially program smoothing. Suarat and I actually wrote one of the earliest papers on this back in 2010, when people would ask, like, why in the world would you want to do numerical optimization over programs? Who cares if the program is continuous and differentiable? But it turns out it's actually a pretty valuable thing to be able to do. And the idea of the symbolic approach is that you have this program, you have an AST representing your program, and you can actually go node by node through your AST, replacing each one of these nodes in a completely syntax-directed manner for differentiable components that approximate the behavior of that component. One of the advantages of this approach is that the smoothed program still preserves the symbolic structure of the original program. You still have something that you recognize as a program. It just happens to be differentiable and happens to behave a little bit different from the original program. There is another approach that has become quite common in recent years, which is to essentially just treat this as a learning problem. Essentially, you have this program. It's just a regular discontinuous program. But now you're going to use this program just to produce large amounts of data. And you're going to use that data to train a neural network to emulate the behavior of that program. So that now you have this neural network that has been trained to behave just like the original program, but because it's a neural network, it's differentiable. You can plug it in to other deep learning infrastructure. You can use it as part of lots of other algorithms that require differentiability. actually, Alex Renda, who just graduated as a student from Michael Carvin's group, actually did an entire PhD thesis on different techniques for neural surrogates and for using neural surrogates and training neural surrogates, including some work that looks at how to exploit the symbolic structure of the program in order to do a better job of creating these surrogates, making sure, for example, that you actually don't miss out on corner cases in the program. Yes.
Could you give us an example of how big these neural networks are, well, these neural surrogates are? Or, yeah, I would imagine that if the program structure is, let's say, sequential, if else, if else, if else, you don't really need a neural network you can do with some other machine learning model.
So it really depends on the application. So to give you an example, one of the applications that Michael Carvin and Alex explored in this space is actually to take an architecture model of a CPU and then create a neural surrogate of this architecture model so that you can use it to explore program optimizations. Right? And so you need a neural network that is rich enough and expressive enough to actually model the behavior of this full performance simulator for a CPU, right? So in general, this is something that you would do when the program that you're trying to create a surrogate for is, maybe some complicated simulation, maybe some very complex algorithm that might be difficult to represent, even just to manipulate symbolically to do something like this. Yes.
What will happen if you start with a program, then you find a neural surrogate, and then you distill it into a program?
We're actually going to talk about that in a second. Yes, so that is actually a really important design pattern and an important combination of these algorithmic building blocks. Usually, just to answer the question very briefly at this point, sometimes what happens is, the neural network is intended to be a surrogate of this program, but it's not necessarily going to be exactly the program that you're looking for, right? And often that kind of back and forth is actually very useful in terms of helping find both a neural network and a program that behave in ways that you want them to behave and that generalize in ways that you want them to generalize. So, we'll get to that in probably about 15 minutes. So yeah, basically this is kind of in picture form of these two kinds of strategies, whether you're doing it symbolically and you're just replacing node by node every one of the components in your program for differentiable components, or you're just using the program to produce data that you use to train a neural network. At the end of the day, the effect is the same. The effect is that you end up with an artifact that approximates the behavior of the original program. It's not going to be a perfect match simply because the original program was continuous, the new thing is now, or the original thing was discontinuous, the new thing is now continuous, but it can help you use this in the context of a pipeline where differentiability might actually be quite useful. And so already with these two building blocks, we can start talking about our first combination of these two different approaches. And so this was a paper from Swarat Chaudhuri's group, and they presented an algorithm called NEAR based on neural admissible heuristics. And so the key idea behind this approach was as follows. So you want to synthesize programs, but you want to synthesize programs that have some numerical parameters that have to be optimized. And so what you're going to do is you're going to start with a simple type-directed search. So in this type-directed search, you start with a hole or with a program with some holes, and then you expand it, all the possible constructs you can put in those holes that are compatible with the types. And anytime you get a complete program, you can test that program. You can say, hey, is it good enough? No, this program is not good enough. This program is also not good enough. But now I have this program. Okay, satisfies the type system. It still has a hole here. I don't actually know what is the function that I'm passing to map. Here's another program. This one has two holes here. I don't know what the body of this function is. I don't know what this other thing is going to be. So now I have to make a decision about which one of these am I going to expand first? Which one is the most promising? How am I going to expand it? And so here's where the really clever part of this algorithm comes in. So we're going to take this program, and we're going to do a symbolic relaxation. So for example, this map, we're going to replace it with some differentiable version of map. And any time where there's a hole in this program, so we're going to plug that hole in with a neural network, right? So after we do this, we can actually then train this whole thing end to end with all the data, all the examples we had, to try to make this as good as it can possibly be, right? So now what we have here is this differentiable representation of not just of some program in this space of possible programs here, but one could argue a representation of really the best program that you might be able to get out of this space. And so the idea here is that once you finish, there's going to be some error term of how well this manages to fit the data that you have. And that training loss can now be used as an admissible heuristic to guide the search. So what do we mean by that? So the heuristic is said to be admissible if it never overestimates the cost to reach the goal. And so what is the cost of a completed program, right? So I have this completed program. There's usually some structural cost that you impose on this program. So you can think of these as maybe a prior over programs that allows you to say, yeah, this program and this other is better than this other program, right? Even if they fit the data just as well, structurally, maybe this one has lots of branches and I don't like branches, whereas this one is more likely to generalize. So there's some structural cost to your program. And then there is a loss term, an error term that just tells you how well your program approximates the data. And so if I have a partial program, what I'm going to do is I'm going to have some structural cost for the partial program. And then I'm going to take these partial programs, I'm going to relax this program, and train it as much as I can. And so this is going to give me some loss. And the claim here is that under some, arguably pretty strong assumptions, this for any possible completion of this partial program P star, the loss that I'm going to get from that completion is going to be greater than the loss that I get from my relaxed program. Now, what are some of those assumptions? Essentially, it boils down to your ability to actually do optimization over these spaces, as well as the expressiveness of the neural networks that you're using to plug in those holes, right? So if we think of the space of possible functions, here's a subset of that space that corresponds to the functions that are expressible in my neurosymbolic domain-specific language, right? And so if my neural networks have high enough capacity, I can pick a space of functions from those neural networks that is going to be a superset of the functions that I can express in my with my DSL, right? And so what that means is that if my optimization is able to find me a really, the best function in that space, which of course is a very, very strong assumption, but in general, if it's able to do a good enough job of optimizing over that space, I'm going to get a function that is either going to be, as good as the functions in this space, or potentially even better than the functions in that space, right? Because my neural network can represent all the functions in that space and then some, right? And then some extra functions. And so what that means is that we have this inequality, right? The loss that we get from the plugging in the neural network and optimizing it is going to be less than the best loss that I can get from the programs in the much more constrained space of programs given by my DSL. And so based on that, I can now just use an A-star search. I just have this priority queue of current leaf nodes, and I can sort them based on this quantity. And at every moment, I can pick the top program with the highest possible score, right? And if this program is already a complete program, it means that none of the other programs has any chance of ever giving me a better score than this program. Again, under those fairly strong assumptions, right? But if it's not a complete program, I can expand it. I can evaluate all those nodes. I can put it in the priority queue. And so, again, this is a guarantee under this very strong assumption that about the expressiveness of your neural networks and your ability to actually search over that space. But if that is satisfied, then this will actually return the optimal program. And the tighter this approximation is, the more aggressively this is actually going to prune the space, and the better it is going to be at helping you find the program. The other big advantage of this algorithm is that you can stop it at any time. And essentially what you're going to get is this hybrid of a program that has some program-like structure, but also has neural networks in the middle. It also has the advantage that this works even if your components or your building blocks have numerical parameters that have to be optimized in order to get the correct solution. So it's actually a pretty powerful algorithm that has been used in a number of domains. Here are some results from the original paper comparing NEAR with A-star with a number of other baselines, and you can see that it's able to find a lower cost program much faster than many of these other algorithms. Yes.
So how many parameters are there in this neural network? I guess the reason I'm asking is I'm a little surprised that you need, in order to evaluate each of the solutions in each of the leaves, you need to train a whole neural network, right? And usually a lot of these enumerative synthesis techniques, a lot of the success comes from the fact that you can very quickly evaluate your candidates, say on input and outputs, but training a neural network with many parameters, I guess if you do it on a GPU, or if it tends to be a much more expensive operation. So how does that?
Yeah, so generally, whenever you're searching, there is this trade-off between how much effort you put into evaluating a decision at every given time versus how many decisions you can do, right? SAT solvers went through this, I guess now a couple of decades ago, where they realized that actually doing things really, really fast can sometimes beat being very deliberative and spending a lot of time on each decision. Sorry? Yeah, so in this context, you have similar trade-offs. And what you find, for example, is that if you use very small neural networks, right? Very small, simple, multi-layer perceptrons for your neural network, you can often train them very, very fast, especially if you have a GPU. They're not going to satisfy the requirements of the heuristic, but they will actually often work pretty well. You can always put in bigger neural networks, make them more expressive, potentially get better guidance, but at the expense, as you point out, of having to spend a lot of resources on the training. So this is one of the important hyperparameters that you often have to play with this kind of algorithm. What is the smallest, simplest neural networks that you can get away with and still get good enough guidance to actually find the solution quickly?
Thanks.
So I think I did not understand something. Can you go back to this picture with the two regions, like the neural network? Yeah, just and the other one. Yeah, and the bigger. Okay. So when you try to find a solution, you get a solution in the brown region. It may not be a program, so you start recursively to do some search, but it will never become a program because in the brown region, but not in the red region.
That's right.
What do you do at that moment? Because you got something optimal, but it's not realizable.
That's right. But as you continue the search, right? So if we go back to this picture, right? So let's say that you evaluate this and you get a score of 10, right? And then you take this one, you do the exact same thing, you plug in the neural networks, and you get a score of 15, right? So it's a higher error than this one, right? But maybe this one got 10 by picking a neural network that is completely unrealizable on the DSL, versus this one got 15, but actually the neural networks were pretty close to a real program, right? So it might be that this one is the better one. So what happens? So it means that your heuristic is kind of misleading you a little bit. You will think that this one is more promising than this one. But this one, you will expand it, right? And you will start generating concrete programs out of these, right? And some of those concrete programs eventually are going to be just concrete programs with no holes that you get to evaluate and say, like, yeah, this is good, or no, this is not good. As you impose more structure in those programs, even if they still have holes that the neural network can apply, now you have more program around those holes. The scope of the computation that is being done by that neural network is now reduced. So it is a heuristic at the end of the day, and you might very well end up wasting lots of time searching this branch when the true thing is on this branch. But it does ultimately, you're going to get to concrete programs that you're going to be evaluating concretely. You're going to be expanding these different branches, and you're going to get eventually to your best concrete program.
So if I understand correctly, you are not looking for the brown region that is as big as possible, but actually as fitting as possible. So you would like to have a brown region that is very close to the red region.
Yes, and this is where some of the practical trade-offs come in, right? So from a theoretical perspective, all you need in order for the algorithm to be correct, right, and to give you a guarantee that is going to give you the optimal solution, is for this brown region to be really large, to cover the red region, and ideally also generally, the bigger your neural networks, the easier they are to optimize. So the more likely it is that you're going to reach an optimal solution. But in practice, from a practical perspective, that's actually not going to be so useful. First, as we said before, it's going to be super expensive to optimize. You will potentially be generating these programs. Essentially, so actually, Raz wrote this paper many years ago on angelic programming, right? And using angelic non-determinism to guide your search of a synthesis problem. You can think of this as another iteration of that idea, where now your oracle is this very expressive neural network, right? So all the neural network is telling you is like, yeah, it is possible to fill in a function in there that will give you the right solution. Now, whether that function exists or it doesn't exist, that you'll figure out as you keep refining your program.
I have a very basic question. I am not a program synthesis person. So what is the your input? Closer to your mouth. No, but I am not a program synthesis person, so this is like program synthesis 101. What is the input to this process? You have examples of inputs and outputs of the program, and what is the notion of the right program? You are talking about finding the right program, but what makes it right? Is it fitting the examples is all you need, or do you need more?
That's a really good question. So this algorithm is going to work very well where your goal is to fit a large number of examples, a large number of input-output examples. Once you have that capability to find programs that match a large set of input-output examples, you can rely, for example, on counterexample guided inductive synthesis to solve other kinds of problems that for which you might have more symbolic specifications, but you're generating that data, those examples, in order to now generate this inductive synthesis problem. For a lot of these kind of problems, you're not necessarily looking to exactly match all the examples. You're trying to minimize some error terms. So you're looking for a discrete program structure that minimizes the error term.
So I also have just a small comment. Again, it's not my domain, but since I think we are all worried that this is very expensive. So I wonder if I imagine you can reuse some of the networks, like even, for example, you have an if then else, and on one branch, probably, I'm just curious if you could reuse the train networks even across search choices in the tree, or even when you expand, out of curiosity.
So this is not something that has been explored, but it is something that you could do essentially instead of starting with random weights at every point. For example, if you've used a neural network for that hole before, you can start from the weights that worked well from that point, right? And you might have to fine-tune them a little bit to get because you're changing other parts of the program, you might not be able to completely reuse them, but oftentimes just starting from a good initial point in the optimization space can actually give you a big advantage. Russ?
Could you go to the slide with the map and fold expansions? Here, right. So let me suggest a different interpretation of this is doing, right? So you learn your neural net for the map choice and for the fold choice, right? Mm-hmm. And then you proceed with the one that is more precise, has less loss, right? So the different interpretation may be that you are trying to predict which of these derivation branches is realizable or not. Since you don't disagree, why not train that unrealizability directly? Because that would be the value, right? You kind of, by applying map, you created a subproblem. Now you would like to know whether that subproblem is solvable or not. And training that directly, wouldn't that give you a better network, better predictor, or we are stuck with really learning a function and then somehow hoping that the error in the function translates into realizability?
So in the case of map, for example, map has actually the very nice property that you can take the inputs and outputs to map, and you can turn them into inputs and outputs to this function argument, right? And in fact, there is prior work that has done that in a completely symbolic way with propagation rules that convert the input-output examples that are global to local input-output examples for this expression. The nice thing about this approach is that it works in a very general way, even in cases, for example, like fold, where the output of this component, this unknown component, feeds into itself, right? And there is this compositional aspect to it, where it would be very hard to kind of individually come up with a set of constraints for this function, this expression over here. But when you plug in a neural network there and you have your kind of differentiable approximation of the whole thing, you get this end-to-end optimization problem that you can solve. And essentially what it tells you is, like, does there exist a function that when I plug it in here, does there exist a function that when I plug it in here, the end-to-end error of this is going to be small, right? That's essentially the question that you're asking here. You're using these neural networks as an oracle to say, like, does there exist a function that could be plugged in there that would get this to do the right answer? Now, because of what was said before, just because that function exists doesn't mean that it exists in the DSL, right? And it might very well be a very bad choice. But for sure, we can say that if that function doesn't exist, then maybe it's not such a good idea to spend lots of time trying to search for it.
Rather than learning, rather than asking, does there exist a function which when you serially compose with each other to obtain a fold, do I get something close to the result? Instead, learn some predictor of, given the subproblem, does the DSL express such a function? So essentially seeing, you know, if the pattern of input-output is such, then I'd like to know that DSL will never express that pattern, so don't go down the fold way. But maybe that's a harder problem to learn.
Well, that's basically what you're doing here, right? This is what the value function in this RL context does, right? You're basically training this value function to look at these partial programs and to look at, you know, in the case of these languages, it's also looking at the state that those partial programs produce. And it's trained to learn, like, does this look like a program that could be completed to the output that I want to reach?
So which of these do you recommend and when?
It depends. This one works very well for these domains that are very transparent, right? Where you can look at the partial state, for example, and say, oh, yes, this looks like it's going in the right direction. So, for example, these drawing domains are very, very good for this kind of setup, right? You can look at the partially completed drawing and you can already see, like, yeah, this looks like a halfway drawing of the thing that I want to draw. This is not going to work very well for something like arithmetic, right? Where you look at the expression, you look at the numbers that it produces, and, you know, who knows whether that's the right expression to get to where I want. Yes.
Since the specification is a set of finite examples, if your DSL always has if a guarded command, you can always find the function. I mean, there is always exists one that can fit your examples. So yeah, this is.
Yeah, so this is something that one has to be careful with this kind of approaches, and oftentimes this is where the structure term in this the structural cost becomes very important, right? Where you want to penalize those programs that just have lots and lots of branches, and because yeah, you can always keep adding branches and eventually fit your entire data set, but it's not going to be a very good program.
Okay, let's move on because Armando still has plenty of things to show us. So, but I'm really happy that there are so many questions and discussions.
Okay, so the next pattern I want to talk about here is distillation, right? So here the idea is you train the neural network. This can be particularly valuable, for example, in cases where the initial neural network was not necessarily trained with input-output examples. Maybe it was trained using reinforcement learning to satisfy some very high-level goal. But you found your neural network, it kind of does what you want, but you want to translate it into a program with some very specific structural constraints, right? And here, the structural constraints are very important because often the question around this is why? Like, you already have the neural network, it already does what you want. What's there left to do? Right? Why would you want to turn it into a program, right? And so sometimes it's because you want to verify it, right? These might be just too difficult to give to the verifier, but if you can distill it into a simple enough representation that you can actually push through a verifier and you can get verification. Sometimes it's all about some properties that you can enforce structurally. By the structure of this program, you can guarantee that it's going to have certain properties that you cannot guarantee about this blob of neurons that you have here. And so I want to give an example from a paper we did back in 2020. This was led by Jivan Inala, who is now at Microsoft Research. And so the problem that we started with here is coordinating collections of drones, right? You have some drones over here, have some other drones over here, and maybe they want to swap spots, and they have to coordinate both with the different groups in order to make sure they don't collide, but they also have to coordinate within each group to decide like who's going to go to which spot in the end, right? And so to give you a sense of the kind of tasks that we were looking at, these tasks were not super complicated, right? You have these little groups of drones moving around. In some of these cases, they already have predefined like exactly where they have to reach, and it's just about making sure that they don't collide with each other. In other cases, for example, like this one, there's just some locations, and they have to agree with each other which location each one of them is going to take, so that they don't both try to go to the same location and end up leaving some other location empty. So turns out that back in 2019, there was a paper that showed how to you can do this using attention. So essentially, the way this worked was that you have agent J, and it has its own internal state as J, and it has some observations about every other agent. And based on that, it has a policy that decides on the message that agent J is going to send to agent I. And so then agent I has its own internal state, its observations, it comes up with a communication policy that decides which of these messages it's going to pay attention to. And so it's going to communicate with all the other drones. It's going to get their messages. It's going to combine them based on these attention weights to get a new vector that is going to pass to an action policy that decides what action to take. And so one of the things that we want here is we want to make sure that we don't have a lot of communication. Ideally, we want every agent to be paying attention to only a small number of other agents. And so the question here was, well, we started from the observation that these didn't work so well. It worked very well in terms of actually doing the coordination. It didn't work so well in terms of minimizing these messages. And so what if we replace this with a program where by construction, we can ensure that this attention is very, very sparse, that at every step, we're only paying attention to a very small number of other robots, so that we only have to go and coordinate with a small number of robots in order to get their messages to compute the policy. And it turns out that you can do this. Here's actually how the communication matrix looks like from that prior work. Here's how the communication matrix looks like after we distill those neural networks into a program in this very specific DSL, where by construction, we're ensuring that there's very little communication going on at every step. And so, yes, in some ways, like both the neural network and the program that we synthesize, they're both programs, but we have a lot of control over the structure of the new programs that we're distilling that allow us to get this property that we didn't have before. The language is actually quite simple. It has a small number of primitives that allow you to first define regions, and these regions are parametric. They're essentially represented as polynomials. And then you can filter for agents in that region, and you can select randomly from agents that passed the filter. And so, for example, here's a policy where you can actually see the region and how it evolves as you execute. And at every step, it's choosing randomly from the agents that make it past that region. Right? Here you have another example where you again see that the communication is basically limited to this region. You can also map some other function over all the agents that pass the filter, and then actually pick the agent that maximizes that function. And so, for example, here you can see that it's always communicating with the agent that maximizes that function. And so when you do this, what you have is you have, in terms of performance, I guess the resolution is not very high, but basically at the high level, this is the loss, so smaller is better. Here's our program. Here's the transformer. Here are two other baselines. And what you find is that the performance of these two tends to be quite similar to the transformer, not a significant loss of performance. But in terms of communication, you can see that the transformer is communicating significantly more than the more symbolic program, right? So, yes.
So when you're distilling, you're only looking at the input-output behavior of the neural network, right?
Yes.
Okay. I mean, there could be some. This is just because I've been thinking about like looking at mechanistic interpretability and that kind of literature, where to look at the intermediate states, and that might give you some clues as well about what to synthesize.
So that's a very good point. So in this case, we are not looking at the, we're treating this learned policy as a black box. We're looking at the input-output behavior of this black box. And based on that, we are searching for the program that has, that most closely matches this behavior. Now, that close match is actually going to be still pretty far from the original policy. We kind of want that. We don't want it to be exactly the same because we want it to have these extra properties. One thing that you have to do in order for this to work is that once you find your, the best possible program to fit this, then you have to retrain all the other boxes in order to actually get something that works end to end. Hey, now.
Just another question on this.
Yes.
You're distilling here into a deterministic function, or you're still probabilistic?
It's probabilistic. One of the things that we found actually for this domain is that the probabilistic behavior actually allowed us to get away with a significantly less complex function. It allows you to actually communicate broadly with many different agents, but at any given time, you're only communicating with a small subset.
So my thought relating to this was that probably the probabilistic function, if you distill to that, will be more fault tolerant than a deterministic function would be.
Yes. Now, in general, when you do distillation, one of the big challenges that you run into is, okay, so you have a goal, and now there might be many different networks that satisfy the goal with similar levels of performance, right? There's lots of policies that you can choose that kind of all of them work pretty well. But not all of them behave in ways that are expressible as a program in the DSL, right? It might be that this one actually can very readily be distilled into the domain-specific language. It behaves in a way that is very consistent with that language, whereas this other ones, even though they are, they do just as well in the tests, in the environment, they don't map quite as readily as this one to a program in the DSL. Now, what does that tell us about them? One thing we might infer, if this DSL actually captures a lot of the regularity in the domain, it might be that even though all of these work just as well on the tests, this one might generalize much better, right? Because the behavior does have this structure that none of these other ones have. And so what do we do if the network that we got in the beginning was this one? Right? And we can try really hard, and maybe we can find some program here that kind of sort of works, but not really. And this is one of the big challenges that you run into when you have this. And one of the ways we deal with this is by combining distillation with something that goes in the other direction, where you have this symbolic guided deep learning, right? And the idea is that you want to train a neural network, but you want to provide, in addition to the goal, you want to provide this additional information that you're looking for something that has some of these structured, captured as a partial program or captured by this domain-specific language, right? So we want to learn a neural network whose behavior is constrained to match some unknown program, right? And we might not know the full program, but maybe we know the DSL from which the desired program is built, or maybe we know the modular structure of the desired program, or maybe we have a sketch of the desired program. And so how do we make it so that we can find train the neural network in such a way that is going to be consistent with this program? And so we can use these two things in tandem in order to actually get what we want. So for example, one of the ideas we presented initially in this paper back in 2020 is this idea of adaptive teaching. So at a very high level, what's the idea? So you have a goal. You train a neural network based on that goal. And so from this neural network, we're going to distill the best program that matches the behavior of this network. It might not be a very close match. In fact, it probably won't be a very close match. But it's a program. It's in the DSL. It kind of approximates the behavior of this network. So at this point, the network is the teacher, And here, the synthesizer is the student who's trying to learn to mimic the behavior of the teacher. But it's not doing a very good job. So now the teacher has to adapt, right? We want to go back to the teacher and say, well, the way you're doing it, the student is not able to learn that. So you need to adapt your teaching. Can you adjust yourself so that you still satisfy the goal, but in a way that makes your behavior closer to the behavior of this program that we found? And the notion of closer here is critical, right? Because we might not necessarily want to just mimic the behavior of this program. The behavior of this program is bad. If it were good, then we would have solved the problem already. The behavior of this program is not very good, but there might be some features of the behavior of this program that we want the neural network to capture because they tell us about the kind of functions that are representable in that DSL. And so now we have a new neural network that we trained that way, and we can use that to produce a new program in the DSL, hopefully a better program, one that is able to more closely match the behavior of the neural network, right? And so you can keep doing that again to now use the information in this program as regularization when you're training this neural network to get behavior out of the network that captures the features that make these representable in the DSL. And so that eventually you get to a neural network that behaves in a way that can be captured by the DSL, right? And so now this is kind of a very abstract idea, right? There's a lot of details here of, well, how exactly do we train a neural network to satisfy these requirements, right? What do we mean by closeness? And so there's a growing literature looking at different ways of using these programs in order to actually steer the training of the network, essentially adding additional loss terms to the neural network to force the kind of behavior that is going to be representable in your DSL. Now, more broadly, when we talk about this symbolic guided deep learning, you might want to do this not just for the purpose of distillation, but as a goal in and of itself, in order to get a model that has properties that the original big monolithic neural network that you were training did not have. And so I want to talk very briefly about two different examples where by forcing the neural network to have a certain amount of modularity and by forcing some requirements at the interfaces of those modules, we can actually get something useful. So the first setup, this is in collaboration with my colleague Wojciech Matusyk's group, where one of the things they have is they have these little modular robots where they can put them together and they can train these monolithic controllers to get these little robots to do something. And it's very nice and very neat. The problem is you build a robot like this and you train a controller for it and you have it crawl around and you find that, you know what, 4 legs is just not enough, right? I need to carry a little bit more weight. I would really like to have one that has 6 legs, right? Well, I have this controller that works for a 4-legged robot. It has just the right number of outputs to go to each of the actuators of these robots. This is not going to work for this robot, right? It doesn't type check. It's not the right kind of module. But if I could, instead of learning one monolithic controller, if I could learn something that has this nice modular structure where I have a module for this leg assembly, and then I reuse that same module for this leg assembly, And then I have a main controller here that just gives high-level commands to each of these. Then I could reuse this module for this robot, right? Sure, I have to retrain the main controller, but the main controller is simpler. It only has to send these high-level commands to each one of these modules, and it doesn't have to deal with the low-level details of how to actuate each one of these legs, especially if the legs become more complicated. So, okay, so instead of learning one big monolithic controller, I'm going to learn this modular structure, right? You can think of these as I have a sketch that tells me what the structure of my program is, and I'm just using this neural network to fill in the details of what happens here. What's the problem with this? Why is this not trivial? There's two failure modes when you try to do this, and they have to do with the interface between these two modules. It turns out you have to impose some kind of structure at the interface of these two modules, because otherwise you might end up with a situation where the global controller does too much, right? You can have a situation where this one is just doing the same thing that the original big monolithic controller was doing, and these ones are just pass-through wires that connect to each one of these things, right? Then sure, you'll get your modules and you'll get your main controller, but the modules are not doing anything, and you get absolutely no benefit from this structure. You can also have a situation where the global controller does too little, right? These get overfit to a particular task, and they're giving all the commands to these legs, and the main controller isn't actually doing anything, which means when you go to another task, when you have a different robot, retraining this is not actually going to work. It turns out that that's not such a big problem, because these local controllers don't have the global visibility of the task that you're trying to accomplish. They're just getting instructions from the main controller here. So this is not such a big problem. This is a big problem. We need to have an interface here that actually imposes the restriction that prevents these from doing too much work. And essentially what we want is, just like when you're designing an API, you want to make sure that your API has a narrow interface, right? That it doesn't, that it's simple commands that let you do what you want, but doesn't allow lots of extra information to flow through. And so it turns out that, well, let's see, we don't have a lot of time. So maybe I'll jump really quickly through the details. There is some secret sauce that allows you to make sure that the Jacobian for this module is very low rank. So what that means is that when you train it, you can pass a signal through this to get the motion that you want. But if you do some perturbations on this, they lead to relatively small changes in the output, right? The alternative, when you don't use the secret sauce, is that you have, sure, you train this model, it does the right thing, but these has so many degrees of freedom that any little change to the input causes some big change in the output, which means that you have too much control over the actuation of the module. It's not restricted to the simple motions that you need to accomplish the end-to-end task. You have too much flexibility in that signal, and the bottom line is it works pretty well. And what's really cool is that the same idea that allows you to train these robot controllers in a very modular way can also allow you to understand the RNA binding proteins that participate in RNA splicing. Unfortunately, I don't really think I have time to talk about this, but I'm happy to tell you more in the break. And so maybe the thing to do is to stop here and ask if there are questions.
Thanks, Armando, for this wonderful tutorial. Let's see, are there any questions? Like, we were definitely asking him lots of questions during, yes.
So what you've been talking about producing as the output here is a program. I think from the point of view of this community, what would be interesting would be to generate not just programs, but programs accompanied by proofs of their correctness. So is there any sort of work in that direction as yet?
So, especially in the context of distillation, for example, a lot of times the goal of distillation is precisely to generate these proofs, right? And in fact, in some follow-up work to that adaptive teaching paper, we actually generated proofs of the, well, we used an SMT solver to prove properties of the distilled programs that you couldn't have proven for the original code. In addition to the proofs, oftentimes, you can't prove what's not true, right? And oftentimes, the neural network, it's not just that it's hard to prove that it has property, it's that it doesn't have the property, right? And it's precisely through some of these ideas that you can push the object that you learn to have enough structure that it actually has the property that that you are interested in. I don't know if that answers the question.
If we take the example of this adaptive teaching, let's say, we see that there are these loops where we train a neural network and then we improve the program and so on in the loop. So is there something that we can learn from how the neural network improves or teaches the program so that we could completely skip the step of the neural network and improve the program synthesis?
So one of the things that you have when you are in that loop is that you're combining these two very different modes of learning. When you're in the neural network side, you're learning entirely through numerical optimization. And you're learning through in this completely numerical way. Whereas when you now go and construct the program, you're building this discrete structure through this combinatorial search process. So it's somewhat difficult to match what you're learning on the neural network side and apply it in the program. On the other hand, one of the things that you do have is that you are solving repeatedly many program synthesis problems, right? And so there's certainly an opportunity. I haven't seen anybody do this, but there is certainly an opportunity to, for example, have some of these neural-guided learning neural-guided search approaches in the loop as you are searching for this program so that you can learn from the programs that that you did at every iteration, right? And I think one of the messages that I want to convey, fortunately, I didn't get to talk about this part, but all of these different building blocks are generally acting together for a whole, right? So for example, when you're doing distillation, you might be using program search, right? And you can use all the different varieties of program search in order to do these distillation more effectively. When you're doing distillation, you're using the symbolic guided deep learning in order to find in this adaptive teaching loop, find a better network that gives you a better program, right? You can use relaxation in the context of program search. So it's this combination of these building blocks what gives you a lot of expressive power when trying to find the right algorithm for a job.
Before, when you talked about distillation, you mentioned that networks we can distill into a symbolic program are more likely to generalize. Could you explain that intuition and maybe whether it holds for all domains or better for some domains than others?
Sure. So part of the idea is that if there is some regularity in the domain, then you can capture that within your domain-specific language in a way that might be difficult to capture with the neural network. So just to give a handful of examples of that, one comes from our own work where we were looking at repetitive behavior, right? Tasks that require repetitive motions. Think of, so our canonical example was like parallel parking, right? So you kind of have these, I move back, I move forth, I move back, I move forth, and you have to keep doing this in a repeated manner. Or imagine loading a dishwasher, right? You grab a plate, you rinse it, you put it in. You grab the next plate, you rinse it, you put it in. You grab the next plate, you rinse it, you put it in. If your DSL captures that repetitive structure, then you're going to get that repetitive structure in the behavior. What you find is that when you just train the neural network with the goal, you end up with something that, if you trained for things that require 1, 2, or 3 steps of repetition, you end up with something that is going to work pretty well when you require 1, 2, or 3 steps of repetition. And then the moment that you have something that requires 4, it's completely lost, right? It doesn't know what to do because it doesn't have this structure that tells it how to work. In Suarez's group, they actually had another paper where they were looking at control problems, where in the structure of the program here, they imposed a certain set of requirements that forced you to get a particular kind of controller that was fairly stable and predictable. And so you would see the difference between the neural controller, which was very jerky and making very arbitrary moves, compared to the controller that gets distilled, that has much more predictable motion, much more predictable behavior, because by construction, that regularity was built into the DSL.
Okay, so let's stop here and let's thank Armando once again. You can still asking questions. One reminder, please, no foods, no drinks. That also means coffee, if anything's happened, Moshe and I will be in trouble. So please, we shouldn't see here coffee cups or anything because you're putting us in trouble. So that we asked you yesterday, so let's stick to that, please. Thank you. And the next talk will be on Zoom. So again, we meet Zoom because that Sandra was another victim of air travel. So we meet again here at 11:30. So break now.
Thanks, everyone.